Welcome students. So we want to discuss about representation of functions as power series. So now let's answer the following question. Can the following f of x can be written as a power series? So to look at that, recall the geometric series. So let's work on geometric series. Summation n equals to 0 to infinity of x to the power n. So consider this geometric series. This is 1 plus x square, so on and so forth. Yeah. So first term is, which is usually written as a, is 1, and the common ratio r is x. So it converges if absolute value of x is less than 1. And what is it equal to? And is equal to a upon 1 minus r, which is 1 upon 1 minus x. So we have managed to write down what? We have managed to write down 1 upon 1 minus x. Now think about it other way around. We have managed to write down 1 upon 1 minus x as this infinite series. And note that in this case, we have this is true only if absolute value of x is less than 1. So this function is written as this power series when absolute value of x is less than 1. So let's deal with the same way with our function f of x. So our f of x is 1 upon 1 plus x, which is same as 1 upon 1 minus x, and that is equal to summation n equals to 0 to infinity. Instead of x, we have minus x to the power n, which is same as summation n equals to 0 to infinity minus 1 to the power n x to the power n. And this converges again, this converges when absolute value of minus x is less than 1. That is same as absolute value of x less than 1. So this power series, so this function here, so the function, this function here is written as a power series like that, and this is only true when absolute value of x is less than 1. Okay, so now we are going to use this to have a representation of function as a series. So let I be the interval of convergence for power series, summation n equals to 0 to infinity cn xn. Then for every x, let f of x denote the series, summation n equals to 0 to infinity cn x to the power n, if x belongs to I. Then we call that summation n equals to 0 to infinity cn x to the n is a power series representation of f of x. Now note that it's important that when you are representing your function as a power series, it should converge at that point. Otherwise, does not work out. So so we will use in this lecture, we will use this series to our advantage. Namely, we'll use this series for all the computations. Okay, so let's see about that. So here we have f of x equals to 1 upon 1 plus 4 x squared. Now what I'm going to use 1 upon 1 minus x is summation n equals to 0 to infinity x to the power n. So let me convert it into that form. or I can think about it as 1 upon 1 minus box equals to summation n equals to 0 to infinity box to the power n, and this is valid as long as valid if whatever is in the box, absolute value of that is less than 1. Okay, so we don't need to write this work in general. So I can write this as 1 upon 1 minus 4 minus what? Minus of 4x to the power 4x square to the, and now in the box we have minus 4x square. So this is going to be summation n equals to 0 to infinity minus 4x square to the power n, which can be written as summation n equals to 0 to infinity minus 4 to the power n x to the power 2n. Now it's a good idea to separate. So this can be written as summation n equals to 0 to infinity minus 1 to the power n, 4 to the power n, x to the power 2n. And now we need to find out the interval of convergence, right? So when you're writing a function as a power series like that, immediately you should say, where is this kind of expansion valid? So find interval of convergence. So now find interval of convergence. Yeah, even though the problem is not asking you to find interval of convergence, you need to basically find the interval of convergence. Why is that? Because if you represent the power series, if you represent a function as power series, you need to say for what value of x is this representation valid. So this holds this, so star, let's call this, so star holds if absolute value of 4 minus 4x square is less than 1. That is, absolute value of x square is less than 1 by 4. That is, absolute value of x is less than 1 by 2. So therefore, this is true when absolute value of x is less than 2. So this formula is valid for when absolute value of x is less than 2. Now observe that if x equals to half or minus half, if you have x equals to half or minus half, your series is summation n equals to 0 to infinity minus 1 to the power n, 4 to the power n, minus plus or minus half to the power 2n. I'm taking both of them together because I have power 2n. We know that that will basically make it minus 1 to the power n, 4 to the power n divided by 4 to the n, which is going to be summation n equals to 0 to infinity minus 1 to the power n. That diverges. Yeah, why? Well, you can use one of the many tests, like you can use the divergence test, for example. Therefore, the interval of convergence is minus half excluded to half excluded. So this means that this formula is valid. So for A, this formula is valid. Star is valid only when your x belongs to minus half to half. So let's look at the next problem. B, we have g of x equals to x upon 9 minus x squared. Now this can be written as x upon 1 by 9. I can take 9 out as well. What I have is 1 upon x minus 3 the whole square. This is going to be x over 9 summation n equals to 0 to infinity x square. So this is your box right here. Yes, so instead of x, you have this thing here. So this will become x square by 3, the whole square, the whole power n, right? So this will become x by 9 summation n equals to 0 to infinity x to the power 2n divided by 3 to the power 2n, and that can be simplified to summation n equals to 0 to infinity x to the power 2n plus 1 divided by 3 to the power 2n plus 1. Yeah. Now again, this result holds. This holds for absolute value of x by 3 the whole square is less than 1, which implies what? X square is less than 9, which is possible if only if x is absolute value of x is less than 3. So this is true for absolute value of x less than 3. Again, at x equals to, now at endpoints, when x equals to plus or minus 3, you can look at the series and see what do we get. The series becomes summation n equals to 0 to infinity plus or minus 3 to the power 2n plus 1 upon 3 to the power 2n plus 1, which is going to be summation n equals to 0 to infinity plus or minus 1 to the power n 2n plus 1, which diverges. So therefore, interval of convergence is equal to minus 3 to 3. So now we want to basically have term by term integration and term by term differentiation of the series. So suppose you have power series from n equals to 0 to infinity of Cn x minus a to the power n, and it has radius of convergence r greater than 0. Then consider the function f of x defined by this series. And this function is differentiable. So you have what your radius of convergence is r. So that means you have a minus r, you have a plus r, right? So in this region here, your function is differentiable. So it is differentiable on interval I, and the derivative is given by n equals to f prime x is same series, but you take term by term derivative. So you're differentiating term by term, differentiating term by term. Yeah, because now you can write, say for example, here you'll have your take derivative on both sides here. So if you take derivative on both sides, so differentiate on both sides, we get what? F prime x. So now what, let me write down the term in the expanded form. So I have f of x equals to c0 plus c1 x minus a plus c2 x minus a squares dot dot dot. So when I take f prime x, what happens is it will be, the first will become 0, right? So this part will become 0, and we'll have c1 plus 2c2 x minus a dot dot dot. So you are basically applying derivative inside. So you have summation n equals to 1 to infinity c n. Now what is derivative of x minus a to the power n? Is n times x minus a to the power n minus 1. And note that it will start from n equals to 1 instead of starting from n equals to 0. Similarly, if you integrate term by term, you will get what? So integration will be, this is same as integration of n equals to 0 to infinity, integration of x minus a cn x minus a to the power n dx. This is going to be integration n equals to 0 to infinity cn x minus a to the power n plus 1 divided by n plus 1 plus a constant c. So you're doing term by term integration and term by term differentiation, and the radius of convergence remains the same. The radius of convergence is r. So let's look at the following examples. So first, A, we have f of x equals to 1 upon 1 minus x squared. And the idea is we want to think about it as a differentiation of a known function whose power series is known. So notice that this is same as d by dx of 1 upon 1 minus x. So we know that 1 upon 1 minus x is summation n equals to 0 to infinity x to the power n, and this is valid for absolute value of x less than 1. So differentiating on both sides, we get d by dx of 1 upon 1 minus x equals to summation n times x to the power n minus 1. Now note that it should start from n equals to 1, not n equals to 0. So please notice the difference. The reason for that is the first term became 0, and this is all still valid for absolute value of x less than 1. And on the other side, you have derivative of this is 1 minus x squared. So the power series for 1 upon 1 minus x squared is this term here. Now let's look at basically g of x, b. So we have again g of x is ln of 1 plus x. Now how does it relates to a known series? The known series we have is, for all these purposes, the known series we are going to use is 1 upon 1 minus x. Yeah, so we are going to use this series for all the problems here. So here we can get, this is same as integration of 1 plus, but we have already established what is the series. This series is, so it's going to be integration of, we know that this series is summation n equals to 0 to infinity minus 1 to the power n x to the power n dx. And this is valid for absolute value of x less than 1. So this is going to be equal to, now limits and in the summation and integral can exchange in the region of convergence, not otherwise, x to the n dx. This is going to be summation n equals to 0 to infinity minus 1 to the power n x to the power n plus 1 divided by n plus 1 plus a c. Now we need to find out what is c. So for that, notice if put x equals to 0, this will give us, will imply what? Ln of 1 is equal to summation n equals to 0 to infinity minus 1 to the power n, 0 to the power n plus 1 upon n plus 1 plus c. So this implies c equals to 0. And therefore we get ln of 1 plus x equals to summation n equals to 0 to infinity minus 1 to the power n x to the power n plus 1 divided by n plus 1. And this is true if absolute value of x is less than 1. So now let's look at the next example. Again, we have to make, so we have C, we have h of x equals to tan inverse or arctan of x. Now this is known as 1 plus by x squared dx. Now we already know that, but 1 plus 1 by x squared is 1 upon 1 minus of minus x squared. This is going to be summation n equals to 0 to infinity minus 1 to the power n x to the power 2n. Yeah. Now integrate on both sides, and this is valid when your absolute value of minus x squared is less than 1. That is, absolute value of x squared is less than 1. That is, if absolute value of x is less than 1. So it is still valid for absolute value of x less than 1. Now integrate on both sides. So therefore, we get tan inverse of arctan of x equals to integral of 1 by x squared dx, which is going to be summation n equals to 0 to infinity minus 1 to the power n integral of x to the power 2n dx. Now note that I brought the integral directly inside, and this is valid if only in this scenario. What scenario? Absolute value of x is less than 1. So now if I write this, this is going to be summation n equals to 0 to infinity minus 1 to the power n x to the power 2n plus 1 divided by 2n plus 1 plus c. Yeah, but now we need to find out what is c. So put x equals to 0. This will give me arctan of 0 equals to summation n equals to 0 to infinity minus 1 to the power n x to the power 2n plus 1 divided by 2n plus 1 plus c, and you took x equals to 0. So this will mean 0 equals to 0 plus c. Therefore, c equals to 0, and we get the formula for arctan x as summation n equals to 0 to infinity minus 1 to the power n x to the power 2n plus 1 upon 2n plus 1. And note again, as I said, this is only valid for absolute value of x less than 1. Yeah. So this is how we can find out the power series representation of certain functions.